Well, hi again. This is Bob, and I'm over about a third of the way down on page, excuse me, 390, and we're getting ready to talk about something called the population proportion. And it has an abbreviation or a symbol of just P. And from the reading, which hopefully you've done ahead of time, but closely afterwards, if not, they tell us at the beginning of that little section there that the population proportion is usually, it can be expressed as a percentage, and it usually means that we're talking about some type of situation. And for example, we might say that, well, 30% of all students are receiving financial aid. Or in the example that they used, they were talking about the proportion or percentage of pleasure boats that were called Serenity. And it turns out that for that example that they said the population proportion was 12%. And of course that would be 0.12 as a decimal, or it could be written as 12 over 100, etc. Or it could be written as, you know, as a fraction, 3/25, they tell us also. And they tell us that, and this is really important because this is, we're getting back into our Z tables, they tell us in that same section in the reading on 7.3 that the proportions can also represent probabilities. And they tell us that if a pleasure boat, using their example, if a pleasure boat is selected at random, the probability that it's called Serenity would be 0.12. Well, here's the idea, and I feel, I don't know how it is on your end, but I feel I've had more confidence in what I'm saying when I show you the formula and then go from the elements in the formula to how they're arrived at and what their symbols mean. But I'm just going to briefly tell you what's happening because it's so familiar to what we've seen before, especially in 7.1, because we're going to be back again using our Z tables, which we were introduced to in Chapter 6. But here's what we're going to do. We have a population proportion, which we call P. That's like 12% of the boats are called Serenity. But what we're going to do is we're still in confidence intervals, and there's something called P hat. And P hat will be a sample that we take from the population, and it can be expressed as a decimal or a percent or even a fraction. And from that P hat, we're going to set up a confidence interval, which will be a certain amount confident, like 90, 95% or 99%, in which the true population mean is contained. And this may sound familiar to what we did when we had I lost my pen there, when we had a sample mean, and we set up a confidence interval to approximate or have an interval to approximate the a population mean. So that's the idea of this section, and we've got to get a few definitions, but fortunately these do not involve a lot of higher mathematics. They really are just definitions, mostly dealing with percents. So again, the first thing I'm going to do is skip over to the next page. I'm going to kind of work backwards here. And like we had a correction on the standard deviation, the population standard deviation, I'll just go back a little bit. You remember that we had something that was called an error, and we put a correction that looks something like this. Oops. And we called that our maximum amount of error, our sample error, something of that nature. Well, it turns out we have that very same idea when we're dealing with the proportions. And it turns out now notice the Z alpha over 2 is the same, but now that gets multiplied times, I don't really need the parentheses there, but I guess out of habit I use them, but I'll follow the books there. We have something inside there called p hat times q hat all over root n. So these may look just a little familiar here. Okay, well finally, and again you'll have to do some reading, but I'll try to hit as much of the theory as possible. Remember, the idea here is to find out this p hat, this sample, population, this sample proportion, and we're going to try to relate that to the true population proportion, or what we call the population proportion. And we're going to do that by setting up a confidence interval by using our z-tables. And our formula, and again, this should look a lot like stuff we've seen before, is our sample, that's like where our sample mean used to be, times z plus z sub alpha over 2. And then we've got the square root business here, p hat q hat over n. And notice that the n must be rooted. Okay, that n is inside the square root. So, and on the other side, p hat q hat over n. This little circumflex or carrot looking thing, when we see this is called p hat. This is kind of like a hat here. Okay, well, we know what the p is. That's the true percentage or probability or population proportion, if you will. And again, we're setting up a confidence interval, just like we did in 7.1 and 7.2, and we need some definitions here. So we only need 2 definitions, and I'm now back on 7.3, about 2/3 of the way down, where they have a little data box, and it says symbols used in proportion notation. And the first one, P, is what we're going to use to set up our interval, and that's called the population proportion. That you can think about, if you like, is sort of like it's comparable to our population mean. Okay, then we have this p hat. Good time to lose my pen. I'm just going to cross that out and write it again. This is called p hat, red p hat, and that is our sample proportion. Now, that is all that we need to use this formula, because we're going to see that q hat and p hat are related. The last one I need to do is q hat. And if let's just look at their example to use that. And I'm just going to give you a situation first, then I'll summarize it. Let's say that we go out and make a sample. We run into, let's go to a campus and do a good sample, and we find that 30 students out of 150 that we survey are receiving financial aid. Well, this would be the same as 3/15, or 1/5, or 20%. So we would say something like 20% of the students are receiving financial aid. Well, if that would be our p hat, then 20%, or 0.20. Now, the way we would find our q hat would just go 1 minus 0.20, and that would be 0.80. In other words, if we know p hat, we subtract p hat from 1 to get q hat, and vice versa. Okay, so now the formula that they give us looks a little more involved, but that's basically what's happening. They tell us that p hat is equal to a given, what we're calling the probability of something happening, x, like 30 students out of 150. Okay, so, and again, as an example, p hat equals 30 out of 150 equals 0.20. Okay, now then they tell us that now they've got a rather involved formula here for Q hat, but Q hat is defined as n minus x over n. Okay, which or much simpler, Q hat. Again, I hate it when this stuff gets wordy, but fortunately the formula is easier to use than saying it. So let's go back and use this example again. You can use their example also if you like, but I said that p hat was equal to 30 out of 150, and that of course would be equal to 0.20. We could quickly, using the best formula, find Q hat by going 1 minus 0.20 and getting 0.80. That's the simplest and most direct way to find it. Or they have an intermediate formula that says Q hat would equal n, which was 150, minus Rx, which was 30 over 120, excuse me, which was 30 over our sample size of 150. And of course that would give one. This is the one that we don't really need to use. So 3 would go into 12 4 times, and 3 would go into 15 5 times, and that would give us Q hat equals 0.80. Okay, well, there's two things that they tell us. If we know p hat, we subtract it from 1 to get Q hat. If we know Q hat, we subtract it from 1 and get p hat. And, of course, that makes sense that they're complements of each other. So p hat and Q hat always add to 1. Okay, well, that's the wordy part of this. Let's go look at the, I just really don't like the middle definition there. Let's just go look at example 7-8. And we're going to shortcut this because I think we don't need that middle definition there. A random sample of 150 assault victims in a large city found that 45 took no self-protection actions against the criminal. Find p hat and Q hat. So in this instance, our x would be 45 and our n would be 150. So p hat, or our sample proportion, would be 45 over 150, and of course as a decimal that would equal 30%, or 0.30. So the minute we know that p hat is 0.30, we would go Q hat equals 1 minus 0.30, or Q hat equals 0.70. We don't need to go through that intermediate step. Okay, so I hope by now we have a little idea of what we're doing. We're going to take a sample proportion, p hat, and we're going to use that sample proportion along with our z-tables to set up a confidence interval in which we believe, or we will be a certain level of confidence, 90th, 95th, or 99% confident, in which the true proportion lies. Okay, so I broke this into two parts just to make sure that we get everything. We don't mix up that second idea with the first idea. The second idea is sample size. But let's just take a look at example 7-9. And it's over on page 392. And I'm going to write our formula one more time. Oops. Okay, so in this case, it tells us Sallie Mae and Gallup, they took a poll of 1,404 respondents, and out of the 1,404 respondents, 322 students paid for their education by student loans. Find the 90th confidence interval of the true proportion of students who paid for their education by student loans. All right, well, here's what we've got to find. We've got to find P hat, and we've got to find Q hat, and we need N. And of course, I already know from the previous section, or excuse me, from 7.1, that the Z sub alpha over 2 for the 90th percent confidence interval is 1.65. Okay, so let's find P hat, and it was 323 out of 1,404. And I'll take the book's word, that's 0.23. Well, if we know that P hat is 0.23 and that Q hat and P hat are complements of each other, 1 minus 0.23 or 0.77 would represent the students that did not pay for their education by student loans. We had a rather big sample size, which was, where's that thing at? 1,404. Okay, and recall that we've used the same pretty much confidence intervals over and over again. We are ready to set this thing up. And again, make sure that you crank through the equation or the interval. Don't just set it up and assume that you can work it out in all situations. Every calculator is different, and it's so easy to make an error on these. Set it up correctly and make a computational error. Okay, so our P hat was 0.23, and to that we're going to add 1.65 times the square root of, I like to use parentheses here, 0.23 times 0.77 all over 1,404. That's the amount we're going to add to 0.23. And for on the other side of the equation, we're going to have 0.23 minus 1.65 times the root of 0.23 times 0.77 over 1,404. So we're 90% confident that the true population mean, according to their calculations, lies between 0.249 and 0.211. Or you could express that as a percent. It would be 24.9% and 21.1%. Okay, now notice that we started off, I've already explained that's our confidence interval. We started off with a P hat of 0.23, okay? And notice that we didn't really add or subtract to 0.23 dramatically, but we did set up a confidence interval. But in this case, we're only 90% confident, okay? If we wanted more confidence, we would use larger z-values, of course, z alpha sub alpha over 2 values, and that would also stretch out our interval. All right, well, I've got one more of these to do because you should see how close they are to our former 7.1 material. This is on self-driving cars. It's example 710. And it tells us that they surveyed 6,000 adults, and 58% said they would take a ride in a fully self-driving car. Again, we're using the 90th confidence interval of the true proportion. Well, this one, they've given us a bit of a break here. This is a sample, by the way, and we know immediately that p hat is 0.58. So q hat, I don't know why this computer, I keep losing my pen here, but q hat, of course, would be 1 minus 0.58, or q hat equals 0.42. Remember, they're complements of each other. And we've got a rather large sample size. The sample size is 6,000. And since we're using the 90th confidence interval again, remember that that critical value is 1.65. Okay, well, we've got all the information we need. It's just a matter now of going into our formula. The true population proportion would lie between, we had 0.58. Shoot. And again, you don't need to use parentheses, but I found out that it's really helpful for me when I'm solving these questions as a reminder, order of operations type thing. My previous computer had a much larger screen. All right, that's supposed to be 6,000 on the bottom, on the left side there. Our true population proportion, we're 90% confident of the true population proportion lying in between 0.591, not a very big correction, less than 0.591 and greater than 0.570. Or as a percent, 59.1% and 57.0% on the low side. I'm trying to circle these, but I keep losing the pen here. Okay, well, to interpret this, they say, hence, we can say with 90% confidence that the true percentage of people who would take a ride in the self-driving car is between 57% and 59%. Now, remember again, we started off with a sample, p hat, which is the sample proportion of 0.58. Notice that we really didn't change it that much. Okay, we added just a little bit to it and we subtracted just a little bit to it. Okay, so like we saw in 7.1, the corrections we put on this are in most cases will not be that dramatic. Okay, I think that's a good place to stop for this first part of the lesson here. And we'll come back and look at the second part, sample size for proportions, where we figure how big a sample we need. And I'll be back with that shortly. Thank you.